Okay, so now we will go discuss the total interval reflection as an application to the Fresnel's equations. So remember what the total reflection is. When the light passes from a denser medium to a rarer medium, it tries to bend towards the normal, okay? And so this is how it happens, okay? So it will bend, okay? So this is my first medium, this is the second medium. Obviously the N2 is smaller than N1. So if the angle exceeds certain value, the incident angle, if that exceeds certain value, this is called theta c, the critical angle, then the theta 2 becomes pi by 2. Okay? So what does it mean? Theta 2 is pi by 2, so that means the wave is fully reflected. Alright? So that's exactly we will be discussing. So this is what we had actually. Remember, this was my theta 0 and that was my theta 2 when we were discussing. So essentially this angle theta 2 becomes 90 degrees. So now if that is so, let's then recall the Snell's law. So according to the Snell's law, we had n1 sine theta 1 is n2 sine theta 2, and therefore we could put the values of these things. So this is going to be n1 sine theta c is n2 sine pi by 2, which is essentially n2. So therefore theta c is going to be sine inverse, and then we will have n2 by n1. So this is the relation number 1. Now let us recall what should have been the value of cos theta 2 and sin theta 2 in case therefore there would have been no total interval reflection. So obviously we already know this is just 1 minus sin square theta 2, which is 1 minus sin square theta 2 according to this law would have been n1 by n2 sin theta 1. So this is n1 by n2, and say theta 1 is basically theta 0, which is the angle of incidence. Okay, so this is theta 1. Okay, so this is n1 by n2 and sine theta 0, n1 sine theta 0 upon n2 and the whole square of these things. Or in other words, we could write this as n1 by n2 according to this one, relation 1 is going to be 1 upon sine theta c, and therefore we should be able to get sine square theta 0 by sine square theta c with, so that's our relation. So now as theta c, so this theta c starts is either equal to theta 0 is either as theta 0 is either equal to 0 theta c or it's greater than theta c. Therefore, what we expect naively that cos theta 2 is going to be square root 1 minus sine square theta 0 by sine square theta c, and that should be essentially, so therefore in fact what we realize is that 1 minus sine square theta 0 by sine square theta c, what should it be? So now because theta 0, when we move beyond along theta direction, sine theta, we will have the values greater than or is equal to 1. So this is going to be, and then we are subtracting from 1, so therefore it should either be equal to 0 when theta c is theta c, or it should be less than equal to 0. So that means, so this is going to be say q, okay? equal to q square, and therefore, in fact, let's say this is q square, and this implies that cos theta 2 is going to be minus q square, which is I times q. Okay. Similarly, we could also define the sine theta 2, which is what? Sine theta is 2 is essentially n2, n1 upon n2 sine theta 0, and n1 upon n2 is sine theta c. So this is sine theta c. So this is 2.2. Okay. So now we will check what should our transmitted wave would have been um, in case we had this kind of situation. So therefore, the refracted wave, what would it have been? So this was E2, and that was basically E2 naught, e to the power I k2 dot r minus omega t. So this is, well, I'm just defining this by something called W. Okay. So this is going to be E2 naught. And now I'm just taking, just opening these things. So e to the power I k2 dot r. So that will have a direction. So this is k2, and this is what we will be looking for. So you assume that this was your z direction, this is x direction, and this is the y direction. So this is going to be k2 x along the x direction, but pointing negative to it. So k2x, and then the angle made by this thing. So this is also going to be theta 2. So this is going to be cos theta 2. And of course, this is going to be a negative thing, plus sine theta 2 plus I k2z. This is going to be z, and sine theta 2. Okay. So that's all we will have. And of course, we will have x and the z direction. And then e to the power minus I omega t. Or in other words, what we realize, this cos theta 2 is basically I times q. So I will just write this as e to the power I times q. That is going to give us, so this is x, this is z. So this is going to be iq. So I square is minus 1 and minus plus 1. So this is going to be e2 k2x, and then we have qx. Okay. And then the rest is going to be e to the power I k2z, and this whole thing is going to be sine theta 2. So this is w, and the z minus omega t. So that means our wave is basically, so that means the wave is traveling along the z direction. The wave has the wave is attenuated, number one. So this is the shifted one. So the wave is attenuated and is moving along z direction. Now let me try to find out the velocity. So what would be the velocity of this? So this is basically width only, and will have a phase velocity. What should it be? So this should be velocity, that's omega by k2. So this is going to c by omega by k2w. Okay. So that's going to be omega by k2w. So omega by k2w, which is omega by k2, and w according to our relation is sine theta 0 and sine theta c. Now omega by k2 is c, so 1 over c and in fact nc sine theta c upon sine theta 0. That's going to be the phase velocity. Now we will try to see what should the amplitude of the reflected wave in the two cases, that is when the electric field is perpendicular to the plane and the second case where the electric field is parallel to the plane. Okay, so for that, so now according to Fresnel's relation, now according to Fresnel's relation, for perpendicular for electric E along perpendicular direction, what we had was this: E1 naught was cos theta 0 minus n2 upon n1 cos theta 2. So this was actually the first case for the oblique incidence. And then n2 by n1 cos theta 2. And then we had E1 naught. So now let's put the value of cos theta 0. So this is going to be cos theta 0. N2 by n1. What is this? N2 by n1 is cos theta. So that's going to be n2 by n1. And cos theta was I times q. So this is n2 by n1. And then cos theta is I times q. This is also cos theta 0 plus I n2 by n1 times q is 0, 0. And therefore, E1 naught is equal to E2 naught. So these are going to be the magnitude for the perpendicular case. Okay. So that's what we see in this case. Similarly, we could also check E1 naught parallel is also going to be E2 naught. You need to basically just check the relations that we had previously for the other case when the electric field was parallel to the plane, and therefore we could also realize, so that means obviously you have the pure electric field. One more thing we could also check is the S2 dot n hat. So let's recall what we will have S2 dot as n hat. So we had C by 8 pi E cross H star. So what was E? So this is C by 8 pi E cross. Then we had, and basically we had then n hat. Okay, I'm sorry. So this is E cross H hat. So this was n hat cross, I'm sorry, C by n by k and k vector cross n hat. Okay, so this is the direction normal to the plane. So h bar is basically E. Okay, so now what I will do is the following. I will try to, and of course then you have dot n hat. Okay, so this should be there. So remember, this n hat was the direction along which the wave propagates. So if we do, so this is n2 in fact. Okay, so if we take that, what I will get is essentially only one term if we solve this triple product, the triple vector product. So this would imply S2 dot n hat is equal to Cn2 by 8 pi k2 in fact, and this is going to be E2. In fact, this is also going to be E2. So this is going to be E2 naught square, and then we will have K2 hat dot n hat, which is going to be, so obviously the other term will be E2 naught cross E2 naught, which is going to be 0. So So these are all zeros. So this is going to get you C by 8 pi K2 E2 naught square, and this is just cos theta 2, which when you solve, this is going to be C by 8 pi in K2 and E2 naught. So now if we put, so this is going to be cos theta is once again I times W. So this is I Cn2 8 pi K2 E2 naught square. Okay, so what it means? So this means, so now what is my T? T is real of S2 dot n hat. Okay, so that's going to be equal to, so this means, okay, so this is T is real of this upon real of S0 dot n hat. Now real of S2 dot n hat is 0, some finite number may be here. So this is essentially 0. So that again confirms that the T, that the R is 1 and T is 0 implies the total internal reflection. However, people have tried a trick to avoid this thing. So what does this mean? So if suppose we have something like this, so then that means if this is coming along this direction, the wave will, so this is the incident wave. It will leave at an angle along this direction, okay? However, what people do, they try actually a trick. So rather than taking this, they actually have something like this. So they, okay, so they rather than getting, they have actually two prisms. Okay, so they put two prisms along this direction. I'm sorry. So then what happens? Essentially, here we have one wave because you had e to the power I to an attenuated wave which has e to the power I. Another will also be an attenuated wave, so you will have actually a T component as well, but that is called frustrated internal reflection, frustrated reflection in fact. Okay, but for now, for you, I think this itself is an enough information. So this completes the total internal reflection part. In the next lecture, we will be talking about the reflection due to the metallic surface as another example of these Fresnel's equations. Thanks for now.